Welcome to ECE 320A. I need to make sure I'm in the right location. This is a little different look than what I was this morning, just a few hours ago. And I'll try to keep track of which class I am in, so remind me if I get off track. I'm actually in the time domain this morning. Today I'm going to be in the frequency domain this afternoon. So and you guys need to be comfortable going back and forth. So whether I'm in the time domain or the frequency domain, you tell me where I need to be. No, don't tell me where to go. Just tell me where I need to be. Anyway, you are going to be responsible for Laplace, convolution, Bode plots, active filters, and three-phase power. That's for the final exam. The final exam is as reported last time. It's on Wednesday, the 18th of December. The next to the last day of finals, and it'll be from 1 to 3, and we'll hold it in this room. And I'll try to give you more information as far as office hours. Unfortunately for you, Kay, we haven't figured out how to clone her. And for that reason, she can't be in two places at once. She's teaching right now. That's why she will not be. We should have done our homework. She won't be helping teach, but she might be helping with office hours. We have to try to figure out what's going to work best for that purpose. Those are the announcements that I'm going to provide today. Not very many, but today what I want to do is try to get us on the same page relative to Laplace transforms. This might be a review. I hope it's still helpful. But you've already covered Laplace transforms, so I'm a little unclear as to how to start, where to go, how to proceed. I thought maybe I would try to get at the beginning and work up from there. That's what I thought. But one thing to get us started was to do a matching quiz. And now you have 4 functions, 1, 2, 3, and 4. And 4 graphs. I need you to match the functions with the graphs, because you're going to need to know this not only in this class but in follow-on classes. You need to be comfortable with and these are unit steps. The u's, that's the unit step function. The argument is what's different. But now, based on these unit steps, which of those match up with A, B through D? So you have 4 graphs, 4 functions. Do they match up, or does one go with all? You decide. Meaning, F1, well, I think I will label the A, B, C, and D with either F1, F2, F3, or F4. Okay? So now I want you to tell me which of those 4 belong with graph A. And I'm going to ask this in a way that will be classroom participation. Everybody brought their clickers? No, I'm going to use your fingers. So you have the 4 fingers, and I'm going to count to 3, and at the count of 3, I want you to display one of 4 possibilities in front of you so that you don't do this and then everybody can see and kind of cheat. I want it to be your answer, and commit. I need you to commit to an answer. When I say A, and then I'll count to 3, I want to see which of these functions should be matched up or paired with graph A. Is everybody clear on the game, the process for the game? Maybe you're not quite clear on how to match these, but you need to be. Okay, by the end of the semester at least, you have to be comfortable sort of figuring out rather quickly which goes with which. Let's start with A. You ready? At the count of 3, I want to see fingers somewhere close so that I can see them. Okay? 1, 2, 3. And it doesn't help when you're doing this. I can't see how many fingers you have, but so kind of show me the lateral view of your, or the wider view of your hand. Everybody's saying C. Which one was what? See, I'm in the frequency domain. Who are you guys? You're in the time domain. I said A, you matched it with 3. So now you're saying that's a delayed unit step with a delay of 2, and that was correct. Okay? What about B? Let's do B. 1, are we ready for B? Okay, 1, 2, 3. I'm seeing mostly even fingers, 2 or 4. Which one is it? I don't know. Let's do 2 and 4, and we'll talk about it later. I don't want to give all the answers away, so now we're seeing F2 and F4. We'll figure out which one is which in a minute before I give you the answer. C. We ready for that one? Well, darn. Okay, ready? 1, 2, 3. That's odd. F1. All right, D. I wonder what it's going to be. 1, 2, 3. As anticipated, it's an even set of digits now. I'm seeing mostly 4s. So let's say this was F4. Now, how are we going to figure out which is which? And the unit step is all based on, basically it's either on or off, and you're going to need to be able to use the unit step not just as it by itself, but also as a switch, so that it's turning different signals off and on at different times. You're going to see U of t used a lot in that way. F sub 3 and A, what you're looking for now is you're basically looking at the argument of F sub 3. You're saying, okay, when is t minus 2 greater than 0? Then my waveform will be on. It will have a value of 1. If you solve this, and now you just look on the independent axis and say, okay, when t is greater than 2 is my F sub 3 on, and it is. Is that clear how you can sort of deduce whether you answered that correctly or not? We can do the same thing for F1. F1 now says, oh, I need the argument t plus 2 to be bigger than 0 for it to be on for F sub 1. So this is now saying, oh, t needs to be bigger than minus 2, and in fact that's what that graph is doing. It's only on when the argument is non-negative. When t plus 2 is greater than 0 for F sub 1. Let's look now at F4 on D. F4 says we want minus t minus 2 to be bigger than 0. So now this one says, oh, we need t to be less than minus 2. And when t is less than minus 2, I just pick a few points. Minus 3, yes, it's on. Minus 4, it's on. So that's consistent with our answer. Finally, then, we can, by the process of elimination, figure out that for B, it's F sub 2. Let's verify that. That's saying that we need 2 minus t to be bigger than 0, or we now need t to be less than 2 for it to be on. And any value of t less than 2, we are at a value of 1. for f sub 2. We good on the unit steps. We can now sort of look at that a little differently. We might now say, well, what if I want to build a waveform and you could scale the magnitude, but let's say this is now g of t. And let's say this is t1 and that's t2. You should now be able to create that pulse out of elementary waveforms where the elementary waveform is a unit step. You've already answered this in the matching game with just a little bit of algebra involved. We could add or combine a couple of those unit steps to produce this pulse. Algebraically add. We could get this piece to go on by saying, oh, I need u of t minus t1 to give me that turn on of a value of 1 at time t sub 1. Then if I want to turn that off, if I want to get back to 0, I could subtract a unit step with the unit step being turned on at t sub 2. Now I could say, oh, let me do this, and this is now minus u of t minus t sub 2. So that g of t, in fact, is, as a function, u of t minus t1 minus u of t minus t sub 2. And now you can generate pulses, unit pulses, with whatever width based on or defined with respect to unit steps. We can carry that a little bit further. Suppose that now somebody wanted to do the following. Suppose that they were interested in this curve, but in fact they only wanted it to be on between 1 and 3. And this curve between those two limits let's say this was t squared as a functional form. If we want to describe just the piece h of t that is non-zero, it's 0 outside of 1 and 3, you could say, well, I don't know, it looks like it's t squared, but now you know how to turn it off and on. You just switch it on between 1 and 3, and you can create a switch with amplitude 1 out of unit steps. You now simply say, oh, I have t squared, and now I can switch that on. That's now u of t minus 1 minus u of t minus 3. And that's now that waveform. Is it starting to, let's do one more. Suppose we had the following. Suppose I now said, here's a line. I'm going to draw the line before I try to label it. Say this is 7 and that's 7. And actually, I only want it to be on so the red is the only piece that I want it to be. So let's call this F6. I'm running out of labels, functions. We now have F6, and I want you to give me a functional form or an expression for that. And you could do that. You could say, oh, it's 0 everywhere else. And what is its functional form there? Assume this drawing is believable. Let's say it's a straight line. Now, what's the expression for that straight line? It has an intercept of 7, and it has a slope of -1. So now I know that I have minus t plus 7 between 3 and 5. And you could then say, oh no, I want to explain that in terms of unit step functions. I could now do this. And if you saw f sub 6 in the bottom row and you go, oh my gosh, I don't know what, I need to Laplace transform that, or I need to figure out what's going on, or what is that functionally, well, you can back that out and just see that it's now the red shape that we defined maybe more clearly in the f sub 6, where it was 0 everywhere other than 3 and 5. We need to get comfortable. Pardon? Is it 7 minus t times, I was hoping it was 7 minus t times that entire square bracketed expression. That square bracketed expression is my switch. It's turning on and turning off. And the only place that it's non-zero, and when it's non-zero, it has a value of 1. Am I doing it wrong? Hope not. All right. Let's now jump back into Laplace. This is chapter 12, which isn't where you started the course. I'm assuming you started the course roughly in the second half of the book, which is chapter 10. And it's logical to start in chapter 9 to kind of get your wheels back up and running with sinusoidal steady state. We will go back and do power at the end. Not of today, but at the end of this little series, or near the end of the semester. That's the plan. But now we're starting then with chapter 12, which is dealing with Laplace transforms. And it's really meant to make our life easier. It's meant to simplify things. And it really allows us to convert from one domain into another. It's allowing us to not have to worry about solving differential equations directly, but solving algebraic equations to solve those differential equations indirectly. We'll go into the frequency domain, do some algebra. Then when we get our final expression, we'll say, well, I need to see that in the time domain. Then we'll inverse Laplace transform and obtain the answer that we wanted in the time domain. That's the idea, is we're trying to now move back and forth from the time domain into the frequency domain, and the purpose of that movement back and forth is that our analysis will be easier. Now it's algebraic. It's like doing 220. It's just now your impedances are complex. Instead of just having all real resistors, now you could possibly have complex impedances floating around, and you play with them similarly to the way that you did with resistors. Here's the definition of our Laplace transform. And it's single-sided or one-sided. That just means we're starting at 0 and going over the positive time axis. We're going from 0 minus, that covers then the origin, or 0, all the way up to infinity. What does this do? This really takes a time domain function, f of t, and weights it in the argument of the integral by a complex exponential. And when you think of a complex exponential, you might just start seeing sines and cosines. When you see e to the st or e to the minus st, s is a complex number, and e to the complex number t is like this rotating phasor, and s is going to be whatever we want it to be. It's the entire complex plane, so that we now collapse time domain information into frequency domain content. You show me a time domain waveform, I'm going to now put that into a different form and give you its frequency domain expression. And maybe the systems that we will analyze will figure out how they enhance or not certain frequencies as they propagate through the circuit. And now if we know what the signal is frequency-wise, and we know how it's being treated with the system, we know what the output's going to be doing in the frequency domain. If we want to know what's happening in the time domain, we inverse Laplace transform. But this is now putting all, what are we doing? We're looking at that function f of t over the entire time horizon from 0 minus all the way up to infinity, and we're weighting that with different frequencies. It's going to be a long day. I'm not yet up. I'm not in shape, okay, vocally. Sorry, I've been talking ever since. Never mind. So, and this is the shorthand notation. We'll just say capital F of S is script L of some time domain waveform f of t. But we are now looking at all of the time history and saying, how is that using frequency information? We're boiling it all down into giving us some new way, some new domain version of the same information. We're now going from time domain to frequency domain. Let's look at an example. Boy, this poor unit step's getting a workout today. But here we are. U of t. And it's doing better than my voice. And this one's starting at 0. We're saying this is the standard unit step. We want to now Laplace transform that. And how do we do that? Well, we simply replace the time domain functional form of the function we're trying to Laplace transform, which is u of t, in that location in the argument of our integral. We just say, oh, that's the integral by definition from 0 minus to infinity of u of t e to the minus st dt. And now we simply need to, somebody want to come up and solve it? You know what it is, right? You know the answer or not? Did you work through this one already? This wasn't on the midterm, everything else was. All right, so let's do it. We now have this integral, from 0 minus to infinity of 1. That's what u of t is. And it's only on from 0 minus to infinity. That's the only time that it's turned on. Then we scale it by e to the minus st. S is a variable. It's not our variable of integration. Our variable of integration is t. We're integrating time out of this. And now you have to remember how to integrate an exponential. And that one's not that hard. So now we have s is just a variable, 1 over minus s, e to the minus st from t equals 0 minus to infinity. Or now we have e to the minus infinity minus e to the 0. And I shouldn't have maybe done it that quickly, but we now have e to the s times infinity and e to the s times 0. And we know what each of those limits evaluate to. What's e to the minus infinity? That one's going away. And e to the 0, 1. So now we have minus 1 over s times minus 1, or we now know that the Laplace transform of a unit step is 1 over s. And we'll maybe just say that's the Laplace transform of u of t. This is now the frequency domain version of that time domain waveform. And the time domain waveform isn't very exciting. It's constant. It's DC. And this frequency domain, you can start thinking, oh, what does this do in the frequency domain? You could start replacing s with j omega and see, oh, that now is just falling off linearly with frequency. As you get higher and higher omegas, 1 over omega is what you're plotting in magnitude, or that's what you're seeing. So higher and higher frequencies do not come through with as much emphasis in the unit step. It prefers low frequencies, and that makes sense because the time domain waveform didn't have much shape to it. It was constant. The unit step is flat. That's DC. What if we looked at a delayed unit step? We now know when that function is on. It's on when the argument is non-negative. The argument is non-negative when t minus t sub 0 is greater than or equal to 0. Or when t is bigger than t0, we know we have a 1 for the time domain waveform. That's u of t minus t naught. We want to now Laplace transform that. And let's just use the definition. That's now the integral from 0 minus to infinity, integrating with respect to time, of the function scaled by e to the minus st. And we're integrating over time. This might look a little different than what we had, but we can make it look very similar if we just do a change of variable. Suppose we said, well, I liked when we were working just with u of tau or u of lambda. Then I felt comfortable with that. I knew that as long as the argument was non-negative, it was on. Let's now replace t minus t naught with tau. And then if we have a t anywhere, which we do in the complex exponential, we'll replace little t with tau plus t naught. And we can now start thinking about the remaining steps for this problem. We need to know then, if we're doing a change of variable, what's tau equal to when t, little t, is 0. We know the relationship. They're just shifted by t naught. If we set little t to 0 and solve for tau, we have what tau equals at the lower limit of our integral. What about what it's doing at the upper limit? You'll let me abuse notation. You know, infinity doesn't really exist as a number, but I'm going to say t is equal to that unreachable quantity. That's the upper limit. What happens to tau? I'm really just trying to find my lower and upper limit of integration with this new variable of integration tau. That's infinity as well. And if I am changing variables of integration, I had dt. I want to see how it's related to d tau. And t naught is just a fixed number. I differentiate both sides and I see that, oh, the differential in tau is the same as the differential in t. So that now I can say, oh, I want the Laplace transform of u of t minus t naught. That's this integral of u of tau. Now my limits of integration, I have tau is equal to minus t naught. This is infinity. E to the minus s, but now I need to replace little t with tau plus t naught, and then I'm again integrating with respect to d tau. I can actually clean this up a little bit if I break that into two exponentials. I have this sum in the exponent, so I can now just say the product of two exponentials. I can say, oh, this is e to the minus s tau, and it's also e to the times e to the s t naught. And s is a variable independent of the variable of integration, as is t naught. That e to the minus s t naught is constant in looks to the variable of integration. I can slide that outside of the integral, or I now can say, oh, e to the minus s t naught is integral of tau equal minus t naught to infinity of u of tau e to the minus s tau d tau. And that argument now is looking pretty good. That's what we just did in our previous Laplace of a unit step. It's looking similar, it's just the limits on the integral have changed. But we can break that apart. We can say, oh, that's e to the minus s t naught. We can split that integral into two integrals. We can say, let's integrate from minus t naught up to 0 minus. That's u of tau e to the minus s tau d tau plus the integral from tau equals 0 minus to infinity u of tau e to the minus s tau d tau. And that right-hand integral now does look like what we just did. We just need to worry about the first integral. How worried do we need to get? We're now integrating the unit step times this complex exponential from minus t naught up to 0. What do we know about the unit step for negative arguments? It's 0. Now we can say, oh, that's 0. Now I'm integrating 0. That's going to go away. And this one is what we expect. That's the 1. And we've already integrated that right-hand side. Let me just go ahead and emphasize the fact that the first piece was 0, or the other one was 1 over s, and now we have e to the minus s t sub 0 over s. And this was the Laplace transform of a delayed unit step. And what's our Laplace transform quantity or expression look like? Is it at all related to what we found for the Laplace transform of a unit step? Yeah, it's a 1 over s. It's just scaled by this exponential, where s is complex but t0 is constant. But we still have this 1 over s shape. That's good. And in general, we've just actually derived a Laplace transform property. If you now delay the argument of a function by some amount t naught, if you knew to begin with the Laplace transform of little f of t, you can immediately find the Laplace transform of little f of t minus t naught. You just take the original Laplace transform, capital F of s, and scale it by what popped out from our unit step delayed expression before, which is e to the minus s t naught. And you can actually prove that general property by just using the definition of the Laplace transform, similarly to how we found or evaluated the Laplace transform of a delayed unit step in the example. I don't know about you, but I'm sure you're enjoying this, so let's do another one. You expect me to see way back there? I think I see a hand in the air. Yes. Can you guys still hear me? Sort of. You'll know to sit more closely. I'm going to run out of juice. Me and the bat and the microphone probably. Go ahead. The question was, in this expression, does this property only work for t naught negative? I'm sorry, positive, because we're subtracting. F of t, so it's a delay. And no, it will work for an advance as well. So t naught could be, but typically we are working with delayed expressions. So this is the more conventional way to think about this result. But if t naught, if you had an advanced function, can we now use this? You would just replace t naught with the negative value. That answer, the question was, can this work for t naught positive or negative? And the answer is yes. Any other questions? But in general, we're going to be delaying things. We won't be advancing, but we can. Maybe on the final we'll advance something. Let's do a Laplace transform of an impulse. Recall what this impulse does when it's under or inside an integral. What's the result of taking this impulse and weighting a generic function, a general function f of t, and integrating from minus infinity to infinity? And we will assume that f of t is continuous. Okay, this particular integral, well, if you know what the impulse does, what does an impulse do, or when is it really active? An impulse is only active when its argument is equal to 0. This particular case, we have an impulse that's right at t equals 0. That impulse is happening right at 0. Everywhere else, it's 0. So you look at this and you go, oh, my integrand is 0 everywhere except at the origin. The only possible thing that could happen is happening right at t equals 0. And in fact, if f of t is continuous at 0, then what you will get is just its value at that time when the argument of your impulse is 0. A lot of zeros going on. But let's look at a different one then. Slightly. What's this integral evaluate to using the same thought process? Think about when that impulse is on or active and when it's off, and how that would influence what you see as a result of performing this integration. When is that impulse going to be on? When the argument is 0, when t minus t naught is 0, or when time t is equal to t naught. That's the only time that this impulse is going to have its non-zero value. That means that it's going to sift out of that integral the value of the argument that it's weighting or scaling at that particular instant of time when the impulse fires or is active. This had nothing to do with Laplace transforms, but we can now use those properties to evaluate the Laplace transform of the impulse. We now want to say, if you have a waveform that is the impulse, what is its Laplace transform? Just like we said, I give you a unit step, what's its Laplace transform? I give you u of t, you give me 1 over s. This is participation now, right? What happens here? What's the result? It's going to sift that argument of the integral that's being scaled or weighted by the impulse and evaluate it when the impulse is on or when it's active. We now say, oh, or can say this is e to the minus s at 0. And e to the 0 is 1. And that's the sifting property. Have any bakers here in the audience? Anybody have a sifter at home? Now you go to the store, you buy your flour, it's pre-sifted. They've taken all the fun out of baking. How can you come sift this flour? Oh, Mom, really? But it builds up a little bit of hand strength, sifting. So now when you think of, that's what's happening, this impulse function is sifting out the argument of that function outside the integral. Just like you were helping your flour, you were getting rid of what you didn't want in your cookies. Yeah, I'll eat the product, Mom. Yes, I will. Yeah, she's a good cook. All right. Laplace transform of exponential. Since you guys are having so much fun, let's work through this. Now I'm going to just allow that gamma, this variable, to be a variable right now. And I'm going to replace that with real numbers, positive and negative, and even complex numbers. So this is going to be a workhorse for us. But we know how to do the Laplace transform. We simply plug the function into its location in the definition of the Laplace transform, which was this integral from 0 minus to infinity f of t e to the minus st dt. F of t in this case is e to the gamma t. And we can combine those two exponents by combining their, or summing algebraically their exponents. And now we have e to the minus s minus gamma times t dt. We've already done this integral when we were doing the unit step. We now have 1 over minus the exponent, s minus gamma, e to the minus s minus gamma t. Evaluate that at the upper and lower limits. The upper limit goes away. Evaluated at 0 minus, we have 1. And we had a minus of a minus, which allows us now to end up with 1 over s minus gamma. And remember, we started with e to the gamma t, not e to the minus gamma t. We just had e to the gamma t. Gamma could be either positive or negative. If you're listening to this at home, we just had a race to a cap, and now I can't get up. I'm teasing. You never know. Never be the same. 1 over s minus gamma. So if you don't come to class, you missed it. You're going, what is he talking about? I don't know. There is our workhorse. We now have the Laplace transform of e to the gamma t equaling 1 over s minus gamma. Now everybody's dropping things just to see. Don't play with me. Well, we can. We can have some fun. We learn better when we're happy. Do you know that? That's why I never got out of school. I was never happy. But anyway, this is a very powerful result. So I'm spelling it out. And as I said, we can let this gamma be real or complex. So let's look at it in multiple ways. Now, try to write this down in a hurry. We have this table, and we're going to use this to actually derive or convince us of the Laplace transforms of sine and cosine. Because we can build sine and cosine from complex exponentials. And I'll make these notes available to you, but you also learn by writing down. And writing is probably better than typing, is what we've been told. Just that physical connection of moving, your brain, watching. You may not want to write all this down, but I want you to start seeing these different relationships or connections with these exponentials. The first row is when we have, let's say, e to the minus 6t, for example, where gamma is minus 6. We're dealing with a real exponential factor, gamma, and it's negative. I hope that's not confusing. Minus sigma, and I'm saying sigma is a positive number, so minus sigma is negative. I never know what's the best way to express that, but I'm hoping this is like e to the minus 6t or e to the minus 4t. What is its Laplace transform? It's 1 over s plus 4 or 1 over s plus 6 for e to the minus 4t or e to the minus 6t. And now you need to be thinking about, okay, what's that look like in the time domain? That's these exponentials. And which ones are faster in terms of their decay? Let's say e to the minus 2t versus e to the minus 10t. Which one decays more quickly? E to the minus 10t is much faster than e to the minus 2t. You just plug in some representative values of time and you'll see how quickly. And you could talk about the time constant of those exponentials. But Now, in the far right, we haven't really talked about that, but you need to get comfortable thinking in terms of poles and zeros. And the other thing that we really haven't explicitly talked about yet is the fact that Laplace transforms can be used for both functions of time, or waveforms, and systems. Meaning, we could have a transform expression, capital X of S, and that might represent the Laplace transform of a signal in time, little x of t. Okay, you've seen that. That's now little x of t is e to the minus 2t, for example. We could now Laplace transform that capital X of S as 1 over s plus 2. It's also possible to Laplace transform or take a circuit into the frequency domain or the Laplace domain and find a representation of that circuit, which we'll call the transfer function. Have you talked about transfer functions? That will now give you another transform expression. So these transform expressions could represent a signal in the time domain. They could represent a system in the time domain, and you can combine them. You can multiply in the frequency domain. That's the beauty of the Laplace transform. The transfer function of the system times its inputs Laplace transform, capital X of S, to generate the output in the frequency domain. If you need it in the time domain, it'll be little y of t. Anyway, where are those poles? These now you're maybe thinking about signals, e to the minus sigma t, but that could also represent the impulse response of a circuit that might have an h of t that is described by e to the minus sigma t. Here, we're looking at 4 different patterns for this, or 4 different values for the variable gamma. We have real, negative, and positive, and the associated transform expression. And we also have complex, upper half plane and lower half plane in the vertical direction for the complex plane. And where are the poles relative to those particular. And the poles are just defined as the values of S that cause the denominator to vanish. We will be dealing with real circuits, polynomials that have real coefficients. All of our zeros and poles will occur in conjugate pairs, complex conjugate pairs. Here we are simply looking at them in isolation and saying, oh, if I had an e to the j omega t and Laplace transformed that, I would just get this 1 over quantity s minus j omega in the denominator, and it has a pole at the value of s where that vanishes, which is at j omega. Now we want to combine these. I said we want to use this workhorse, the Laplace transform of this general exponential, to find the Laplace transform of a cosine and a sine. And the background is your buddy Euler. Euler, this is one of those relationships you just have to feel good about. Right? This is where the sines and the cosines come from these complex exponentials. E to the jx is now cosine x plus j sine x. And for whatever reason, I've put a star beside it, but that's because we want to keep track of it. We can also look at e to the minus jx. And if we replace x with minus x and realize that cosine is even and sine is odd, it now can be rewritten as e to the minus jx is cosine x minus j sine x. Then if you add star and double star, Now you have 3 stars on your refrigerator. I was just talking to someone at lunch and he said, yeah, my refrigerator broke. Oh. I'm sorry. 3 stars on your refrigerator. But now you know what those equal. E to the jx plus e to the minus jx, that's 2 cosine of x. If we combine star and double star, the imaginary component, or yes, the imaginary parts cancel, and now we have our another friend that is all from Euler. Cosine of x is this combination of complex exponentials. That's e to the jx plus e to the minus jx over 2. And we now know how, and if we want the sign, we can subtract. So now you have a negative star on that refrigerator. Star minus 2 stars, a minus star. That was what was on my refrigerator at home. How you got another minus star at school? Really? Don't remind me. Sine of x, e to the jx minus e to the minus jx over 2j. And now we can Laplace transform or find, using our workhorse, the Laplace transform of an exponential, which we worked one of those rows in the table. We now have the way to, and the Laplace transform is a linear operation. We now can combine 1/2 e to the j omega t with 1/2 e to the minus j omega t to find the Laplace transform of cosine. And that was in our table. 2 different rows. We know that the Laplace transform of e to the j omega t is this 1 over s minus j omega. We're scaling it by 1/2. Likewise for e to the minus j omega t. And if we obtain a common denominator, then these imaginary coefficients go away. And we're left with the Laplace transform of cosine omega t is s over s squared plus omega squared. If somebody now says, oh, what's the Laplace transform of a cosine? Hopefully now you feel a little bit better about saying, oh, that's s over s squared plus omega squared. We can do the same thing for, well, before we go on to the sign, let's just look at what that looks like if we look at the poles and zeros of that cosine. We look at the zeros, that's the values of s that cause the numerator to vanish. And that's right at the origin. There's our circle at the origin. We say, okay, what values of s cause the denominator to vanish? Now we set s squared plus omega squared equal to 0, and that gives us then these imaginary values for the poles. Now when you see poles and zeros with this pattern on the complex s-plane and they say, oh, what's the waveform corresponding to this pattern? You now need to just walk up the imaginary axis and find the value of omega and say, oh, it's cosine with that frequency. It's cosine omega t. And does this sort of make sense? If you now wanted to say, well, what's the frequency response of this cosine? What signals sort of does it like? Now when you're walking up, as soon as you get right on top of that j omega, it really goes crazy, doesn't it? Because you're dividing by, that's a pole. So it really favors that frequency of omega, as you walk up the imaginary axis. And that's what I just said. The poles, s squared plus omega squared, equaling 0, and the 0 is when the numerator is set equal to 0, and that's when s is equal to 0. What about the sign? Yo, question. Are we now, is the question focusing on this? Yeah. And now what I'm doing is I'm taking the square root of both sides to find s. So now I have this s squared is equal to the square root of minus omega squared. Now the square root of minus 1 is j. And that's where the j is coming from. And the s is equal to plus and minus the square root of minus omega squared. I think the question was, how did I go between the highlighted yellow and the line below it? But that's just solving for s, which is taking the square root of both sides. Was that the question? Now I should have you derive this one. This is the result. Where are the zeros? There are no finite zeros, are there? And you'll have people talking about infinite zeros. Oh, no wonder I'm running out of juice. I told you. I'll keep talking with my head down. I'll never get my head back up. Excuse me. We back in business, sort of. I don't think you're hearing me very well in the back, are you? I'm going to have to wear a neck brace Thursday because I'm going to be looking like this. How's everybody today? Everybody okay? I'm not, but maybe I'll do this. Keep my head down. Oh. Now I lost my marker. Have no idea how I'm going to continue. Okay. Where was I? Zeros. Oh, and infinite zeros. I was talking about infinite zeros. Have you heard of infinite zeros? Or zeros at infinity? Here you can see that there's no finite value of s that causes that to vanish. That means we have no finite zeros. But if you let s go off to infinity, do you see that that would cause that function to disappear or vanish? And s is it's squared. There's two s's in the denominator. You really have two different values of s that could go off to infinity, so you have two zeros at infinity. That's how some people can say, well, you always have the same number of zeros as you have poles. That's because they're including the zeros at infinity. But here, most of the time, we're just dealing with finite poles and zeros. But if somebody says, oh, what are the zeros at infinity? You can say, well, let me look. And then you're really comparing the order of the numerator with the order of the denominator. In this case, the order of the numerator is 0. The order of the denominator is 2. 2 minus 0. You have actually 2 zeros at infinity. I saw a hand, I thought. Yes?
So wouldn't you have a 0 at infinity with the cosine function too?
So now, if we went back to the cosine, do we have any zeros at infinity? How many? We have 1. So now you're looking at s going to infinity, and now you have s over s squared, which looks like 1 over s. You just have one value of s going off to infinity, causing that to vanish, or causing it to disappear.
Wouldn't you have another 0 at negative infinity?
So now you just have, now infinity is in any direction. Now infinity is like this globe, and you can get to infinity in any direction. You just have 1. So where it is maybe not so important. It's just that its value is infinite. But you still have one finite 0 for this cosine. And that finite 0 is at the origin. For the sine, what's its pole 0 diagram? Now this is X's and O's. We have purely imaginary poles, j omega and minus j omega, and if we set s squared plus omega squared equal to 0, we would evaluate and find those values. Plus and minus j. We're right on the imaginary axis. We have no finite zeros, so we wouldn't put any zeros anywhere. What if I now gave you a waveform in the frequency domain maybe I'll call it X, like that. What does that look like in the time domain? And maybe before we go there, let me just ask you a question that I know you can answer. Where are the poles and zeros? Finite poles and zeros. There's a 0 where? There's a 0 at a finite 0 at s equal to minus 1. S equal minus 1 causes the numerator to vanish, and we have one of those. So we can find the 0 where are the poles? Are you used to seeing polynomials factored in this way? Yes, no, no. So this factorization, which I like, allows you to immediately see the real and imaginary parts to the roots of that quadratic in the denominator. This actually has, now if you looked at this, this actually has poles and zeros, poles at minus 1 plus and minus j2. Yes?
Are there units for the poles and zeros?
So are there units for the poles and zeros? What are the units on S? That's what these are, correct? These poles and zeros, we're saying S equal something. So units on S. And here this is what we were playing with. We know the units on T. let's say it's seconds. Let's say we know it's time. This has units of time, and usually we just think of it in seconds. The exponent needs to be dimensionless. S now has units of per time or per second, and typically we have this having units of radians per second, where radians is dimensionless. But S is a frequency. We'll say, what's our complex frequencies? Where are the poles? So S is now, the poles have units of radians per second. That answer your question? And I said that these poles are at -1 plus and minus J2. They're now stacked in line with that 0 at -1. And the reason I can write them in this manner is, let's just look at this. Let's now solve that. Let's say we have S equal to -1 plus J2 and S equal -1 minus J2. We're really solving for the values of S that cause that quadratic to vanish, but if we solve this or put all my terms on one side, I have an S plus 1 minus J2 equals 0, and this is an S plus 1 plus J2. Here's one of my factors, and there's the other. I have two values of S that cause that denominator to vanish because it's quadratic. One of those factors can be factored as an S plus 1 minus J2, and that corresponds to this pole at -1 plus J2. That can kind of be confusing occasionally. And then the other one is at the pole -1 minus J2. But if I now combine these two and say, oh, I have S plus 1 minus J2 times S plus 1 plus J2. Now do you see where my expression was coming from? Let me treat this as a quantity. I now have, oh man, help me out here. What's the form or the acronym you guys use to keep track, or how to multiply FOIL, thank you. Gosh, you get in front of an audience and you go blank. FOIL, first, outer, inner, and last, right? Doesn't take me in front of an audience to go blank. I'll just a heads up. But now we have S plus 1 squared minus J2 times S plus 1 plus J2 times S plus 1 minus J2 times J2. Or, do you see that the inner pieces, the OI in FOIL, I don't know if I've got them right, I'd just humor me. We now have S plus 1 squared, and J squared is -1. That's why I like to write it in this form. I now can immediately, by inspection, say, oh, that has roots at -1 plus and minus J2. Now you know where that comes from. Clear? Next time we'll pick up somewhere close to this, probably with maybe circuits, and then we'll figure out that we need to inverse Laplace transform, and we'll do all of that sort of together. See you Thursday.